In the blink of an eye, the sun releases enough energy to power humanity for thousands of years. In the time it takes to snap your fingers, the sun produces enough energy to power our entire civilization for 4,500 years. Naturally, scientists and engineers have been trying to replicate that star power here on Earth to fuel our energy grid. And the surprising thing is, they've made significant progress. It might not look like a tiny star in a lab, but it functions similarly. Stars are made up of an immense number of particles that gravity compresses into a super-dense core. This core is so hot and dense that atomic nuclei are forced together, creating larger, heavier nuclei through a process called fusion. This differs from fission, where atoms split apart to release energy. In both processes, a small amount of mass is lost, which, according to Einstein's famous equation, is converted into energy. Since the speed of light squared is such a large number, both fusion and fission release a tremendous amount of energy. In the Sun, most fusion produces helium nuclei. Two protons combine to form deuterium, which then combines with another proton to create helium-3. Two helium-3 nuclei then fuse to form helium-4. However, this first fusion step is exceedingly rare. Only 1 in 100 septillion proton collisions result in deuterium formation. While this isn't a problem for the Sun due to its vast number of protons, it presents a challenge here on Earth. To address this, researchers use a more reproducible fusion reaction. A deuterium nucleus fuses with a tritium nucleus to create helium-4 and a neutron. We've been performing these kinds of reactions in particle accelerators since the 1930s, but accelerators aren't designed to capture the energy produced. They're mostly used to generate neutrons for scientific or military purposes. If we want to tap into fusion to power the world, we need fusion reactors. These reactors would not only harness the energy released but also channel enough energy back into the system to keep the reaction going while sending the excess power into the grid. A fusion reactor would work by generating helium nuclei and neutrons in a superhot core. The neutrons would escape and heat up a layer of lithium, which would then heat water to produce steam, drive turbines, and generate electricity. Meanwhile, the helium nuclei would remain in the core, keeping the reaction alive. However, there are significant challenges, such as containing a mass of matter heated to millions of degrees. But the largest obstacle is reaching what's called ignition. For fusion to be a viable energy source, it must generate more energy than it consumes. Getting the core hot enough for fusion requires an immense amount of energy, so ignition is the point at which the fusion process becomes self-sustaining and produces more energy than it takes to maintain. Stars achieve ignition thanks to the crushing force of gravity, but replicating that on Earth isn't feasible since we would need thousands of times the mass of the Earth itself. Instead, researchers rely on methods like vast arrays of lasers or a combination of magnets and high-energy particles. In 2022, scientists at the US National Ignition Facility made history by achieving ignition using 192 lasers to heat deuterium and tritium to 100 million degrees. While this breakthrough is monumental, we're still far from developing a self-sustaining fusion reactor that produces more energy than it consumes over long periods. However, the potential is incredible. Once operational, these reactors could power a city of 1 million people for an entire year using just enough fuel to fit in 2 pickup trucks. To generate the same amount of energy with coal, you'd need about 3 million tons. That's the power of fusion, virtually limitless energy with minimal emissions. A true source of star power, created right here on Earth.